Hi everyone, my name is Asaf Rosin and I will talk about almost optimal distribution-free sample-based testing of k-Modality. This is joint work with Ilan Aron. Sequence sigma is said to be k-modal if there are at most k peaks and valleys, excluding the endpoints. For example, this sequence has a 1, 2, 3 peaks and valleys. The special case of k equals 0 is unateness, which is just upward/downward monotonicity. And the special case of k equals 1 is the case of unimodality, as in this example. In this talk, sigma denotes a sequence of length n. Our task is to decide whether a given sequence sigma is k-modal or is epsilon far from being k-modal. And we focus on three main things. First, we focus on sample-based testing. We are allowed to use samples, not queries. Our second focus is the distribution-free model, in which samples are chosen according to an arbitrary probability distribution. And our third focus is one-sided error testing, so we must accept if sigma is k-modal. The distance from k-modal is measured with respect to p. That is, the pair sigma p is epsilon far from being k-modal if the minimum weight of symbols that should be modified to make it k-modal is bigger than epsilon. We note that most previous probability testing results are using queries and under the uniform distribution. Since we are focused on one-sided error testing, our actual question is the following. What is the minimal number of samples such that for every pair sigma p that is epsilon far from k-modal, a sample of size s from sigma contains evidence that sigma is not k-modal with probability at least 2/3. The number of samples may depend on the parameters n, k, and epsilon, and the samples are chosen according to p. Previous work. It is known that square root of n over epsilon samples are both necessary and sufficient for testing monotonicity and unateness under the uniform distribution. This raises some natural questions. First, how does the sample complexity increase as k increases? And the second, what is the effect of having a general underlying distribution? I'll try to answer this question during the talk. Our first result is that the sample complexity of distribution-free one-sided error sample-based testing of k-modality is log k over epsilon times a square root of kn. Our second result is that the previous upper bound is almost tight. We show a lower bound of 1 over epsilon times square root of kn. And our first result is completely tight bounds for testing under the uniform distribution. We show that the sample complexity in this case is exactly a square root of kn over epsilon. In particular, our first result fixes claim and argument of Goldreich and Ron for distribution-free sample-based testing of monotonicity. I'll now mention a few related results, and I will focus about related properties of functions over one-dimensional domains. We have a work studied sample-based testing under the uniform distribution, many works which studies query-based testing under the uniform distribution, and another work which studies the query-based distribution-free testing of monotonicity. I will now share some of our observations and techniques. For an integer t, x1 to xt is said to be a t upward sequence if xi is smaller than xi plus 1 for every odd index I, and xi is bigger than xi plus 1 for every even index I. And similarly, we can define a t downward sequence. It just starts with a descent instead of an ascent. In this example, we have a sequence sigma that contains a 4 downward subsequences marked in red. And we denote by ft up the set of all sequences that do not contain any t upward subsequences. Our first observation is that it's enough to upper bound the sample complexity of testing ft up in order to upper bound the sample complexity of testing k-modality. The following structural claim, plays a central role in our upper bound analysis. If a sequence sigma is epsilon far from ft up, then there exist t indices, a1, a2, up to at, starting with 1 and ends with n, such that for every index I, the subsequence from the consecutive subsequence from sigma ai to sigma ai plus 1 is at least epsilon over t minus 1, far from being monotonically non-decreasing if I is odd, and far from being monotonically non-increasing if I is even. The following illustration shows exactly what we are trying to get. We're trying to divide the sigma into such subsequences that are far from non-increasing or far from non-decreasing, alternatingly. And of course, non-decreasing means that there are no downward pairs, and non-increasing means that there are no upward pairs. An important note is that the subsequences are not disjoint, but they overlap. And this is crucial to the correctness of the proof and the claim. Heavyweight symbols might cause difficulties in the case of an arbitrary distribution P. I'll now try to describe the high-level proof idea. So first, we define A2 to be the first index for which the sequence starting with sigma 1, sigma 2, up to sigma A2 is relatively far from being non-decreasing. And here, when we say relatively far, we mean that the distance of the sequence from the property is at least epsilon n over t minus 1. Okay, so it's clear that the distance of sigma 1 to sigma A2 minus 1 must be less than epsilon n over t minus 1 by the definition of A2. And now we suppose that the distance of the rest of sigma from sigma A2 to sigma AT, the distance from ft minus 1 down, is less than epsilon n minus epsilon n over t minus 1. So we can do two things. First, we can modify the first subsequence, sigma 1 to sigma A2 minus 1, so that there are no upward pair in this subsequence. And the cost here is that we have modified less than epsilon n over t minus 1 elements. Next, we can modify the rest of the sequence, sigma A2 to sigma AT, so that no t minus 1 downward sequence remains in it. And by our assumption, we know that we can do this by modifying less than epsilon n minus epsilon n over t minus 1 symbols. So the total number of modification we did was less than epsilon n. And now we claim that no t upward subsequence exists in sigma. To verify this, let's consider this illustration. So first, let's assume that the first upward pair in the t upward subsequence in sigma ends before A2. This contradicts the first asterisk, so it cannot happen. That is, we know that the first upward pair must end in A2 or after A2, but in this case, we consider the rest of the t upward subsequence, and we notice that it must start after A2 minus 1, and it is a t minus 1 downward sequence. So this contradicts the double asterisk. As the total number of modification we've done was less than epsilon n, and we concluded that in this case there are no t upward subsequences in sigma, we conclude that sigma is not epsilon far from ft up, which is a contradiction. The conclusion is that the distance of sigma A2 to sigma AT from being ft minus 1 down is at least epsilon n minus epsilon n over t minus 1. And in this case, we can just continue and recursively apply this idea in order to define the index A3, A4, and we continue like this until we define the entire required sequence in the claim. We now turn to our next main building block, which answers the following question. Given a subsequence that is relatively far from monotonicity, how many samples are sufficient to detect a violation? We begin with some common definitions. First, a pair of indices x and y is called a violating pair if x is smaller than y, while sigma x is bigger than sigma y. Next, we consider the violation graph, where the indices of sigma are the vertices of the graph, and all the violation pairs are the edges of the graph. The vertices are weighted according to p. For a subset of indices S, we denote by a gamma of S the set of neighbors of vertices that belongs to S in the graph G. I will now describe the high-level idea of the analysis. Let C be a minimal weight vertex cover of G. And let sigma be a sequence that is beta far from monotonicity. It is known that the weight of C is bigger than beta. Let Q be a sample of size S according to P. Following the paper of Goldreich and Ron, we observe that the weight of the set of neighbors of C intersection Q is at least the weight of C intersection Q. And why is that? Otherwise, we consider the set C prime, which is defined by taking the set C and replacing every symbol that was sampled by its neighbors, which might not be in C. And we claim that C prime is a vertex cover. And this is true because C is a vertex cover, so every edge in G has one of its vertices, at least one of its vertices lies in C. And either this vertex was not sampled, so it is in C minus Q, or this vertex was sampled, so it's in C intersection Q, and thus C prime contains the other, again, its neighbors, the other vertex of the edge. So C prime is a vertex cover, and as it has a smaller weight than C, which is the minimal weight vertex cover, we reach a contradiction. So the observation holds. Now we know that P of C is big, and thus the weight of the sampled part of C is also relatively big, and by the observation, the weight of the neighbors of C intersection Q is also relatively big. As both C and the neighbors of C intersection Q have large weights, they are easy to sample, and thus it is easy to sample a violating pair, because every edge in G represents a violating pair. But is C intersection Q has a large weight? So in the uniform case, it is true. Every sample that lies in C contributes its weight, which is 1 over n to the total weight of C intersection Q, unless it was already sampled. So by Chernoff bound and by bounding the number of collisions, we get that the weight of C intersection Q is omega of S beta over n. So by taking additional n over S beta samples, we get a vertex in the neighbors of C intersection Q with high probability. This is because the weight of the set of neighbors is, by the observation, at least the weight of C intersection Q, which we has just lower bounded. Thus, we get a violating pair for a total of S plus n over S beta samples. Taking S to be the square root of n over beta, we have a total of square root n over beta samples. And this concludes the analysis for the uniform case. But for a general distribution P, we might have some difficulties because heavy weights might cause a large number of collisions, and light weights contributes less than 1 over n to the total weight of C intersection Q, maybe a negligible weight. To handle the difficulties caused by heavy and light weights, we prove the following claim. So let P be a probability distribution, and let C be a subset of indices. Suppose that the weight of C is at least beta, and the weight of each index in C is at least delta, where beta is positive and delta is at least beta divided by some sufficiently large constant. Then a sample Q of size 1 over square root of delta beta satisfies with high probability that the weight of C intersection Q is at least delta beta S divided by 4. Combining this claim with the argument from the previous slide, we get an upper bound of 1 over epsilon times the square root of n for distribution-free testing of monotonicity. Combining the structural and probabilistic claims, we can obtain that if sigma is epsilon far from ft up, then with high probability, a sample of size square root of tn times log t over epsilon contains a t-1 upward pair subsequence, which has the following form. So we say that a sequence x1, y1, x2, y2 up to xt, yt is a t upward pair sequence if for every odd index I, xi is smaller than yi, but for every even index I, xi is bigger than 1i, as can be seen in this example. Our observation is that the existence of a t-1 upward pair subsequence in sigma implies the existence of a t upward subsequence in sigma. And we prove this by just gluing all these upward and downward pairs in sigma together to get one big t upward subsequence. And this t upward subsequence is the evidence in the violation that proves that sigma is not free of any t upward subsequence. And this establishes our first result, which is the upper bound for the distribution-free model. I will now move on to our lower bounds. Both lower bounds for the uniform distribution and for the distribution-free model are based on the following construction. Let sigma be 2, 1, 4, 3, up to 2m, 2m minus 1, and the rest filled with the value 3m. In the uniform case, we set m to be 2 epsilon n, and every weight to be 1 over n, of course. And in the distribution-free case, we set m to be n minus 1 over 2, and pi to be 2 epsilon over n for each symbol in the downward pairs, and the rest of the weight is equally distributed between the rest of the symbols. Sigma is epsilon far from k-modal, because in order to make sigma k-modal, one must eliminate almost all of these m downward pairs. Actually, all of them except approximately k over 2. To obtain evidence that sigma is not k-modal, the samples must hit at least k over 2 downward pairs. And by a birthday paradox type argument, we get that the sample must be of size omega of 1 over epsilon square root of km. For the uniform distribution, we get a lower bound of square root of kn over epsilon. And for the distribution-free model, we get a lower bound of 1 over epsilon times square root of kn. The flexibility of the distribution-free case allows us to set m to be at the order of magnitude of n, and thus obtaining a higher lower bound. To end the lecture, I will quickly remind our results. So first, we had an upper bound for the distribution-free model, and then an almost matching lower bound. And finally, we have a completely tight bounds for the uniform distribution. Thank you very much for listening to my talk.